Greetings from the Department of ECE, SJBIT. I'm Anita. Today we are going to discuss about another type of antenna, which is horn antenna and helical antenna, parabolic reflector kind. Previous lecture, as we have seen about Aguda antenna, we'll start about helical antenna. This is the basic geometry of a helical antenna. One can notice that wire can be wound like a helix. This is known as the helical axis with respect to the helical axis, and one can see the spacing between the turns. This we call it as a one turn, single turn. The spacing between the turns, which we call it represented it as a S, and whereas the D, capital D, representing the diameter of the total helical antenna, whereas a small d representing the diameter of the copper conductor which you have taken, and L representing the length of a single turn antenna, length of a single turn helical antenna. And total length of the helical antenna, if I want to get, as we know the spacing between the elements as S, if you have n number of elements, if you multiply that with S, obviously you will get the total area, total length of the wire, total axial length. So total axial length will be n into S, whereas the total length of the wire, if I want to get, if length of a single turn antenna is L, likewise if you have n number of turns, multiply that with n, results in total length of the wire. And one can notice from the diagram, you can represent like a triangle representing the circumference of the helical antenna, which is considered as pi into d. Like it is having a three different structures. One is having a like a circle, and another one is having a cylinders kind of, another one is a straight line. So one can notice here representing that circle as having a parameter, circle having a circumference as C equals to pi into d. So as I have told you, it combines three geometric forms. One is a straight wire, another one is a circle, another one is a cylinder kind. And as I have told you, a helical antenna, it consists of a conducting wire which is wound in the form of a helix, and it is mounted over a ground plane. The feed one, which is connected, feed line which is connected between the bottom of the helix and the ground plane. And here you can observe from the diagram, and this is representing the spacing between the turns. And once if you means between C and S, if you draw, then you will get the length of a single turn. From the triangle, the angle between C and L representing alpha. Alpha we also call it as a pitch angle, and it should be from the Pythagoras theorem, L value, if I want to determine, if I know S and C spacing and the circumference, then one can calculate L value by using this formula. And the pitch angle from the triangle, one can say that it can be represented in terms of tan as opposite side divided by adjacent side, S by C, or tan inverse of S by pi into d. So will result in, suppose by varying the alpha, varying from 0 to 90 degrees, one can result the helical antenna into different shapes. Suppose if alpha is 0, that means you are turning alpha value as 0, then it results in a loop kind of. That means how do we can interpret, means alpha 0 means S value is 0. S means there is no spacing between the loops, so it is something like compressed one, so loop antenna will be resulted. And another one, so when alpha is equal to 90 degrees, so if this should be 90, denominator part should become 0, diameter should become 0, circumference should become 0, indicating that you will get a straight line. So two different structures that you can result with by varying the pitch angle alpha. There are two modes in a there are basically two modes, which is a transmission mode and radiation mode. In the radiation mode, again you have three different types based on the circumference. So helical antenna, which is majorly used in as a frequency shifter, polarizer, and as a feed antenna for other types. So it is a basic 3D geometric form, and you will have a three geometric forms that you have: straight line and a circle and a cylinder. And these are the one which I have already discussed: capital D diameter of the helix, circumference if I want to get pi into D, then spacing, a capital S is spacing, alpha indicating pitch angle, L indicating length of a single turn, n small n indicating number of turns. If I want to get axial length, total axial length, n into S, small d indicating a diameter of helix conductor, that is a copper conductor. And if I want to get n into total length of the wire, if I want to get, we can multiply n into L. As I have told, you have two modes, transmission and radiation mode. In radiation mode, based on the circumference variation, you will have three different types of modes again, that is normal mode, axial mode, and conical mode. Based on the circumference variation, comparison with respect to the wavelength of operation lambda. When C is much less than lambda, results in normal mode. Approximately equals to lambda, results in axial mode. When C is greater than lambda, indicating conical mode. This is a diagram representing in all different types of modes how the radiation pattern would be. Suppose if I place the helical antenna along this axis, this is the axis which I have placing, then you can observe in normal mode the circumference of the circle which we are considering should be much less than the wavelength of operation. In such cases, you will get the radiation pattern normal to the axis. So this is the axis, and normal indicating 90 degrees opposite. That means opposite to that, the helical axis. So coming to the axial mode, in axial mode we'll consider the circumference approximately equal to the wavelength of operation. This is the axis which we are placing. One can notice the circumference variation here, and one can notice the radiation pattern which has turned from normal to axial mode. That means along the axis you will have, that means end fire radiation that you will have. So you will by varying the circumference of the helix, one can notice the variation in radiation pattern changing from broadside to end fire. Coming to the next one, which is a conical mode, where the circumference is much larger than the wavelength of operation. Again here you will have a radiation pattern which has been shifted. You can notice the radiation pattern with respect to the axis. Now majorly in helical antenna, majorly will make use these two kinds, either axial mode or normal mode. With respect to the type of mode, you will have different types of polarization. It can be a circularly polarized or linearly polarized antenna. So axial mode, in axial mode it results in circular polarization, whereas in normal mode results in linear polarization. Majorly will make use axial mode type of antenna, helical antenna. And as I have told you already, the helical antenna which is mounted over the ground plane, while connecting the feed also will be connecting between the bottom of the helix, that is bottom of the helix, and the ground plane. The ground plane plays a major role here, and it is the case considered for axial mode, indicating C approximately equals to lambda. and different types of ground planes, which has resulted in variation in front to back ratio. First one, if you observe flat ground plane, here you can notice this is a ground plane and this is a helical antenna. Flat type you have, with that flat type you will get a low front to back ratio. Here you can observe you will have a back radiation also. And if I vary the ground plane from flat type to shallow cup type, so you can increase front to back ratio. That means the back radiation one can eliminate, reduce. Whereas a deep conical type, if I make use, obviously high front to back ratio that you can attain. But if I go with this type of structure, the complexity of the structure also will get increased. So as we have seen about till now the geometry of helical antenna, now we'll look into the different parameters. Any antenna if you design, basically we need to look into what is its gain and what is its bandwidth, what is the impedance. Impedance plays a major role. Suppose if the impedance is not matched with the line impedance, then you will have a reflection, most of the power will be lost. Then coming to the axial ratio which determines about the polarization, as we know that axial ratio is defined as a ratio of major axis to minor axis. Suppose if I consider an ellipse kind of, if this is a center, OA to OB ratio, major axis to minor axis ratio, if it is symmetrical, OA to OB ratio will give you axial ratio, major axis length to the minor axis length. Suppose if OA equals to OB, indicating you will get a circle, that is a circular polarization. If any one of this becomes 0, then it results in linear polarization. Another one, if major axis is greater than minor axis, then it results in elliptical polarization. So axial ratio value, it should lie between 0 to 1. 0 indicating 1 indicating a circular polarization, 0 indicating a linear polarization. Now coming to the different parameters for an axial mode type, radiation parameters. There's a radiation resistance with different types of feeds. Feed indicating input how you are providing. This is for axial feed, where you are giving input to the axis, helical axis. Then this is a peripheral feed. In such case, the radiation resistance varies as first case 140 into C of lambda, second case 150 by square root of C of lambda. With the tapered microstrip line is majorly the impedance variation. In order to eliminate, we can go with tapered microstrip line for impedance matching. As I have told you, impedance matching is one of the major parameter to avoid the loss of signal. Now coming to, as we know that axial mode results in circular polarization, normal mode results in linear polarization. In circular polarization, in order to attain circular polarization, these are the conditions which you need to maintain. So that is circumference, all these parameters C of lambda indicating circumference specified in terms of wavelength, that is C by lambda. It should be between, circumference between should be between 0.8 to 1.2, whereas alpha pitch angle should be between 12 degrees to 14 degrees, and n indicating number of turns, it should be greater than 4 or equals to 4. If you maintain this condition, then you can attain with axial mode circular polarization. Coming to the gain, half power beam width and the directivity parameters of axial mode helical antenna. Half power beam width, as it is defined as the angular separation between the points where the power becomes half, whereas the first null beam width representing it is the angular separation between the points where you will get a first null. That means radiation becomes first time 0. and one can notice relation between these two is 2 times. F and BW is 2 times half power beam width approximately. So 52 by C of lambda into square root of n into S of lambda, whereas this is 115 approximately 2 times. Whereas the directivity you can calculate using two ways. One is, if you know about half power beam width, one can calculate the value as 41253 is one case. Another case is HPBW square in theta direction and phi direction. So whereas 32,400 one can notice or one can make use for a high gain structures or high directive structures. For highly directive structures we go with this type of numerator constant, 32,400. And coming to the directivity, another formula for that means you can make use calculate from circumference and spacing and n as 12 into C of lambda square n into S of lambda square, whereas C of lambda, S of lambda can be calculated as C by lambda, S by lambda. Once if I know, either you can make use this formula or this formula depending upon which one you know. Suppose if I know C of lambda n S of lambda, you can make use this, or if you know half power beam width, you can make use this. Depending upon that one can make use. Coming to the gain, if you know directivity, formula for that gain is n into eta into directivity, whereas eta indicating efficiency, which is how effectively the input power is converted into the radiated power. Suppose usually in case of an ideal one, efficiency should be 100 if there is no mismatch. Then if you have mismatch, obviously if you have some losses, efficiency will not be 100%. Obviously in case of helical antenna or horn, this one parabolic dish antenna, you'll have a 60% efficiency. So you can multiply 60% with the directivity, one can result with gain. So this is a particular case of evaluating a axial mode helical antenna to have the directivity as 24 dBi. They have specified. First convert that into normal value. So while doing a conversion, as we know, 10 log base 10 directivity value is equal to, which they had given as 24 dBi. Now you convert evaluate this one, 24 by 10. So D is 10 power 24 by 10 is 2.4. If you do evaluate, then you will get this value. Now as it is specified, axial mode helical antenna, one can assume C of lambda, S of lambda values as this, and from C of lambda and alpha value in between these two angles, and you can calculate S of lambda by using C of lambda into tan means tan alpha. One can attain S of lambda. From that directivity formula, one can calculate n. So in order to have 24 dB gain, you need to if directivity, you need to make use 80 turns. Okay, this is one of the example, and this is a radiation pattern diagram indicating axial mode helical antenna, indicating how axial mode helical antenna radiation pattern is varied with respect to variation in alpha pitch angle and variation in number of number of turns. One can C of lambda circumference, if you vary how it varied, one can notice. So C of lambda for a particular frequency you can notice, that is for 0.66. if you have, then this is the radiation pattern as C of lambda kept on increased. Now you can notice the radiation pattern bidirectional has been converted to unidirectional pattern, and with a particular n value as 6 turns and having alpha as 14 degrees, one can notice the radiation pattern. If you further increase C of lambda, you will have the back radiation also resulted. Then circular polarization that you can get in between these two. it is between 0.73 to 1.22. If you maintain the circumference, one can result in circular polarized radiation pattern. So here one can notice that vertical that is theta variation and phi variation components, and this is the diagram representing how the radiation pattern varies with pitch angle, maintaining number of turns not pitch angle, maintaining means effect of number of turns. If you keep on vary the number of turns by keeping alpha pitch angle constant. Pitch angle, if I consider as 12.2 degrees, by varying the number of turns from 10 to 2, one can notice the bandwidth. So here and here one can notice the bandwidth, half power beam width, and the bandwidth of that antenna, broadband. And the radiation pattern, it is narrow, and whereas here half power beam width, will be evaluating half power beam width from that directivity. So here in directivity is 32,400 divided by half power beam width square. That means inversely proportional. Suppose if half power beam width is more, in this case directivity decreases. So this is highly directive antenna, highly directive. If you have more number of turns, the directivity of that will be increased. If you have less number of turns, if you make use less number of turns, directivity decreases. This is a diagram showing a radiation pattern having effect of number of turns. And this is the one for a single turn antenna with a pitch angle as 12 degrees. That is indicating a radiation pattern in both theta and phi direction, that is in E plane and H plane radiation pattern, E plane radiation pattern. This is a diagram representing the helical antenna. This is a ground plane, circular ground plane, and this is a helical axis, and one can notice like a helix, conducting copper conductor which has wounded like a helix, and this is a radiation pattern which will be resulted in. So this is along the axis that you have. So it is a axial mode helical antenna which we have resulted in, and this is for normal mode broadside, and this is end fire, that is axial mode. This is normal mode and this is axial mode helical antenna. And these are the helical antennas as already discussed. And this is a feed. As I have told you, impedance matching is one more important parameter. To maintain a feed, we need to evaluate the height of that in a proper manner, which is related to width and epsilon r value, dielectric constant of the slab. So one can calculate from that. So this other parameter, like as I have told you, axial ratio, which is 2n plus 1 by 2n, where capital N or small n one can make use, n indicating number of loops that you have, number of turns that you have, 2n plus 1 by 2n. One can notice here, obviously this should be slightly greater than 1, slightly greater than 1 that you will get. And with this we have completed helical antenna discussion. So which we have started with helical antenna structure, then followed by the modes, different types of modes that you have, and the effect of ground plane, and different types of parameters, how it varies for an actual mode kind, and effect of the radiation pattern based on the circumference variation and the number of turns variation, and for a single turn, multiple turn, then impedance matching, then followed by axial ratio, indicating which type of polarization that it has. Thank you. Hope you have understood. Have a nice day.